It is very often a delicate task to solve balance equations. But there is one particular class of continuous time Markov chains for which it's feasible. This class is known under the name of birth and death processes. A birth and death process is a continuous time Markov chain where in state I, the only possible transitions are to state I-1 and I+1. Let's introduce a few notations. Lambda I is a transition rate from I to I+1, and mu I is a transition rate from I to I-1. For instance, let's consider the MM1K queue, so the MM1 queue, but with a finite buffer of size k-1. The arrival rate is lambda if I is less than k, since in state k the system is full and we cannot accommodate any more customers. The departure rate stays the same, equal to mu. Another interesting example is that of a queue with balking. For call centers, it's a key problem to assess the impact of the impatience of customers. One of the simplest models we can envision to represent this type of impatience is known as an MM1 queue with balking. If there are I clients in the system upon the arrival of a new customer, this customer refuses to enter the system with probability 1 minus 1 divided by I+1. The probability of balking is there to model the fact that not all people react the same way to long queues. This means that the arrival rate is no longer lambda, but only lambda divided by I+1. The departure rate stays the same, equal to mu. However, not all continuous time Markov chains are birth-death processes, even if they are representing queuing systems. For instance, we can have what are called batch arrivals. Imagine a desk at which a group of customers may arrive together. They create the same number of tasks as they are members of the group. Consider that the arrivals occur according to a Poisson process and that, for the model to be simple, we may have one customer with probability P1 and two customers with probability P2. So there may be three types of transitions: I to I-1, I to I+1, or I to I+2. This can be represented either by the transition rate matrix or by the transition diagram. The transition rate from I to I+1 is lambda P1, from I to I+2 is lambda P2. The global balance equations are equivalent to the equality of the global input flow into state I and its global output flow. For local balance equations, we only consider local equilibrium between two states. The local balance equations are satisfied if, for any pair of states I and j, the flow from I to j is equal to the flow from j to I. There is, in general, no reason why the global balance equations should imply the local balance equations. But for birth-death processes, they are equivalent. This means that if we can solve the local balance equations, then we also find a solution to the global balance equations. The local balance equations are far easier to handle since they only relate to pairs of states. The main thing to notice is that the transition rate matrix of a birth-death process is always tridiagonal. We have non-zero coefficients on the diagonal in red, the subdiagonal in blue, and the superdiagonal in orange, and that's all. This is, of course, due to the fact that the only possible transitions are from I to I+1 or I-1. When we write the system πq equals 0, we see that at each line only πi, πi-1, and πi+1 are involved. We can go even further and greatly simplify this system. We see in line 1 that minus lambda pi 0 plus mu1 pi 1 is 0, but we notice that in line 2 we retrieve this very same quantity up to a change of sign. So we can replace this block in line 2 by 0. And line 2 now becomes minus lambda 1 pi 1 plus mu 2 pi 2 equals 0. But once again, this block appears almost as it is in line 3, so we can again remove that block from line 3. And we may proceed likewise forever, and we have a series of equations involving only pi I and pi I plus 1. A small picture showed that these equations mean exactly that the local balance equations are satisfied. The flow between I and I plus 1 is equal to the flow between I plus 1 and I. Now we can solve the balance equations recursively. Rewrite the system by putting pi I and pi I plus 1 on the two sides of the equal sign. From line 1, we get pi 1 as a function of pi 0. From line 2, we get pi 2 as a function of pi 1, and then combining with the previous identity, we obtain pi 2 as a function of pi 0. And we can proceed likewise forever. The result is that we have a rather simple expression of pi I, which is given by lambda 0 times lambda 1, etc., times lambda I divided by the analog product of the mu i's. Since we have an infinite state space, we have a stability condition, which only means that we can find pi 0 such that the sum of the pi i's is equal to 1. We may apply these computations to our MM1 model with bulking. Recall that lambda I equals lambda divided by I plus 1 and mu I equals mu. Using the previous result, we have pi I is proportional to lambda divided by mu times lambda divided by 2 mu, etc. This is equal to rho to the power of I divided by I factorial with, as usual, rho equals lambda over mu. It is known that 1 plus rho squared divided by 2 plus rho to the cube divided by 3 factorial, etc. is equal to exponential rho. So the normalizing constant should be exponential minus rho. This means that the stationary distribution of the MM1Q with bulking is a Poisson distribution of parameter rho, whatever the value of rho. There is no condition on rho to ensure stability, as opposed to the standard MM1Q. Actually, when the number of customers is high, the rejection rate is close to 1, and thus a very few customers are likely to enter the system. There is a sort of feedback which prevents the system from exploding.